Hello, my dear friends. Today we're going to talk about idea of automatic differentiation. That's a very important concept in deep learning and in machine learning. That's actually the workhorse of all these stochastic gradient training algorithms for our modern models. And we'll start with the idea of differentiation and different kinds of differentiation. For example, previously we talked about manual differentiation, so which means actually taking derivatives by hand, which could be fast actually if you will end up with the closed form solution, but any mistake could lead you to a failure in computation of all these complex gradients and Hessians and etc. So we'll skip it. That's not our choice. There are some ways to do the similar thing actually, but with the computers, and that is symbolic differentiation. For example, in Python we have SymPy library where you can input your function like in a symbolic way, like x to the power of 2 plus exponent from sinus and etc. and etc. So using this combination of relatively simple building blocks, you can type in your symbolic expression for your function and receive an answer of, for example, gradient of this function. Also, very known product of this type is Wolfram Mathematica. Wolfram Mathematica. I hope I didn't mistake here, but it doesn't matter actually so much. The problem with this approach is that it could be very slow in terms of computation of very complex derivatives and Hessians, and typically we do not have this symbolic expression of our function where we need to compute these derivatives, which means that this is also not our choice. There is one more way to compute gradients or derivatives. It's actually what is called numerical derivative. For example, imagine that I have a function like this, and we have 2 points here, x1 and x2. And we have 2 function values, which are pretty close in my drawing here, but it doesn't matter. And actually, scalar derivative here is approximately equal to this difference, right? But you have to tend to enforce these points to be as close to each other as possible. And the problem with this approach is that it is a very unstable solution, because here you have to divide by a very small number, and in Python, in any other actually programming language, when we are working with floating point arithmetics, that's bad idea to divide by a very small number. So it is a very unstable way to calculate derivatives. Moreover, to find a derivative of each with respect to each parameter in our model, we have to do this propagation, this what is called forward pass, but we'll talk about it later in the video, twice per each parameter, right? Which is also very long, and it takes time. So that's also not our choice. And that is our choice. That's our choice. The idea, which is called automatic differentiation, and In fact, we're going to talk about the idea, how is it used in modern frameworks, what's the core of this idea, and we'll see some basic examples on it. We'll start with a very simple chain rule in calculus. You probably all remember it. Suppose you have a sequence of scalar functions. For example, you have an input w, then it goes to a function, and you have L as an output here, and this output goes as an input to another function R. So it's very easy to verify that these derivatives dr with respect to dw is actually nothing else but what is written here. And this is pretty simple formula for a scalar case. However, there are analogous in the vector case, when the input of some function is a vector, or even when both input and output are vectors. So let's consider simple example. Suppose we'll increase the dimension in our work here, and we have this t as an input. Then it goes through these two functions, x1 from t and x2 from t. Then it goes to the overall output f from t. And typically, like having a scalar output, it's pretty common for us because we are focused on solving machine learning optimizations problem typically, which require and typically they require minimization of some loss function, which are scalar typically. But we'll consider all possible ideas here. So the formula of a chain rule here will be called, like previously it was univariate chain rule. Now we have multivariate chain rule, and it's very easy to imagine how this formula will look like in case we have not two but say n arguments, right? Imagine that here we have this x3 from t and etc, xn from t and so on. You will have this summation, right, which is actually pretty similar to a scalar product, right, between two vectors. First is containing these derivatives of f with respect to all x's, and this vector with derivatives of x actually with respect to t. So that is this formula. Again, we have n inputs and a single scalar output here, and that's the formula. And actually, this formula could be easily generalized for the case of vector output. We will write this formula for each output of our function. Say we have j output of our function, which now maps from Rn to Rm. And this formula will be still valid here as it was before, but we will place j here everywhere. And we'll have this dfj divided by dxi term, which actually is a Jacobian, right? This is Jacobian, and when we realized that, we can easily write down a vector form of this multivariate chain rule, which means that we have this or this way to compute, to propagate our derivative through this transformation. Again, let us figure it out again. What do we have here? We have here some, say, input t, doesn't matter here actually a lot. And then we have, let's say again we have x, which is n-dimensional vector. We have f, which maps from Rn to Rm. And here, for sure, this has dimension n times 1. This have dimension m times 1. And this is nothing else but m times n, or here n times m. And again, 1 times n and 1 times m. All should be clear here. But what is this formula about, actually? This formula actually allows us to propagate the derivative through some transformation. And that's the core idea of this formula. So imagine that we have some map from like vector space to a vector space, for example, multiplication on a matrix, and let's say linear operator. For example, we could have this function f, which is w multiplied by x. That's an example here. And the Jacobian here is w transposed, right? Because the Jacobian should be of size n times m, according to our notation here. And that's it. Let's take a closer look how all these formulas are connected with the, for example, neural network training or idea of propagating error, which is called back propagation here. Let's take a look on a very simple example of a neural network. But it's actually not a real neural network, because typically we have a long sequence of transformation in a neural network. But here we have very simple linear mapping. After this we have some nonlinear, probably function sigma from z, and later we have a loss function. And let us pose a problem here and formulate an idea how to deal with the problem. Typically, we have this, let's say, x as an input, and this is actually, usually it is a training data set. As well as t in this notation here. This is actually, usually this is labels. Typically from training dataset. But W and B here are the weights of our neural network, of our model, or the parameters, the trainable parameters, and these parameters are needed to be tuned in order to minimize our loss function. Okay, let us formulate it here. Let's say weights or parameters. And actually our goal is to adjust these parameters to find the optimal, in some sense, value of these parameters. And usually we're using stochastic gradient descent algorithm and its variants to solve this problem. What does it mean? It means actually that we update our weight, let's say W weight, iteratively in the following manner. W k, okay, let's write it bigger. Wk plus 1 is actually Wk minus gradient or derivative of a loss function with respect to this parameter W. Probably with some learning rate, right? Alpha k here, which is learning rate. And this thing initially is obtained by initialization, right? We have some W0 at the beginning. So this is initialization. This alpha is hyperparameter here. It should be selected in advance according to some rules and ideas which will be discussed later in our course. This is hyperparameter. Wk plus 1 is next value of our updated weight. So we will calculate this thing. Calculate it. And what is left here is this derivative. This derivative of a loss function with respect to a W value. And that's our goal of the whole idea of backpropagation. We are to find this derivative. If W is a matrix, this derivative is a matrix. If W is a tensor, this derivative is a tensor of the same shape. The same for vector, for sure. But typically, when we are training our neural network, we have something like this. We have some input, which could be a data or some signal, like some sequence and etc. And a sequence of nonlinear transformation of our signal, with hope to obtain something which is close to a label or close to something which we wanted to predict. For example, transformation 1, and if an input, let's say denoted as x in, the output after the first transformation will be, let's say, x1. It could be a vector or a matrix, but typically we are talking about a vector here. But when we are considering images, that's a tensor, and etc. and etc. For simplicity, you may think of x as a vector, just a vector. Second transformation, x2. And typically each transformation here, again, third transformation, and etc. Let's say k transformation. Xk as an output here. And each of these transformation has its own parameter which is needed to be tuned. For example, W1, W2, W3, Wk. There also could be a biases, like for those of you who know what it is, there are also biases, but we do not consider them due to simplicity of our speech all right, of our way to learn this thing. And let's go further here. What do we do? What is the algorithm here? Firstly, we do what is called forward pass, which is just calculation of a loss function. We just take x, we take some value of weights and biases, then we calculate first transformation, then we'll calculate a second transformation, a third, and etc. And actually, the whole idea of this approach is relying on building a computational graph. And computational graph is just a graph with a sequence of nodes. Each of those is just some simple arithmetical operation. For example, multiplication, addition, taking to the power of something, exponential, logarithm, sinus, and etc. It could be a function of several arguments like this. Here we have a function of arguments x, w, and b. You can actually, again, just skip this b. You can set it to 0 and doesn't consider it for simplicity, but still we have it. And typically each of these node, each of this operation is delivered with an efficient way to compute derivative through this simple operation. Again, this is actually what is called computational graph. Computational graph. That's a sketch, actually, of the graph, because typically graph consists of very basic operations, like really basic. Addition, summation, as I said, and etc. And all like subsequent operations are usually splitted to very basic ones. And during our forward pass, this is forward pass, we just compute a loss function at the end. So the goal of the forward pass is to compute loss function. Pretty obvious, nothing special for now. But remember our goal. Our goal is to compute this derivative dl divided by dw. And the idea of calculating these derivatives heavily relies on the idea of chain rule, because we have a sequence of transformation here, of transformations. For example, like imagine that all that we have here are scalars, like there is no vectors at all, only scalars here in our examples. And that's why I can write a very simple explanation of a chain rule here. For example, dl divided by dw is nothing else but dl divided by dy multiplied by dy divided by, let's say, dz multiplied by dz divided by dw, and etc. So we have this form of a chain rule. It's pretty easy to verify, right? That's the correct answer. But the whole magic here is how do we compute this multiplication? And we just relying on a computational graph here. So if we have a computational graph, we can just go from the very end to the very beginning of our process. Here, we firstly compute this derivative dl by dy, which is pretty simple. That's this derivative. And actually, you have a specific value of y and t, which was made during the forward pass. We store all this intermediate information which was used during the forward pass here. And let's say later we have this derivative, dy divided by dz, which is also pretty simple derivative. For example, here is the derivative of a sigmoid function. And you know how to take this derivative is this. And etc. and etc. So the whole idea is to go from the end of your computational graph to the beginning of your computational graph and take all your intermediate derivatives with you and propagate them until the very end of your process. And actually, that's called backward pass. You are computing derivatives here. That's the difference. What is interesting here is that, for example, when we have a real neural network with a very long sequence of layers, activations, and etc., when we computing this one, the gradient with respect to these parameters W1, we already computed all previous, in terms of backward pass, previous derivatives, like dl with respect to dw3, dwk, and etc. Okay, let's formulate this idea. So again, suppose that we have a computational graph, which is a sequence of a very simple arithmetical operations of your mathematical machine learning model here. And each node of this computational graph is just a very simple arithmetic operation. And we'll denote it as V1 from Vn. That graph is ordered graph because we have an order here. We have a first, we have an input nodes, and the overall output node, which is typically a loss function. So we're just computing all nodes as a function of its parents for each node. And that's pretty reasonable, pretty understandable here. That is forward pass. What about the backward pass? During the backward pass, we're starting with Vn, with the last node here, and we compute all the derivatives which is needed to propagate to the very beginning of our computational graph. And again, let's take a look on our notation here. We have the loss function L, which is depending on all intermediate variables, and our goal is to find all these derivatives, which is overlined V here, right? So that's our goal. And actually, again, to find all the derivative, suppose, what do we have here? We have here some linear transformation. Let's say a very simple linear layer, we have a vector, a matrix of weights here, and an input signal x. Here we have linear layer of a neural network. Linear layer means just multiplication by a matrix probably followed by some non-linear activation. Sorry? But we are interested in just linear layer, like even without activation. And that's our output here. And here could be another part of our neural network. I don't know, let's say 100 layers could be here before this linear layer. And actually, the same situation happens after our linear layer. It could be, I don't know, 100, 200, like as many as you want to be here. And like this idea and this approach is very modular because it allows us to compute all this like derivative in a very, as I said, modular way, right? For computing forward pass, what do we do here? Forward pass. Forward pass means just calculating this multiplication. Okay, we just multiply matrix W by vector X and receive a vector Z. Super okay, that's it. What is backward pass? Remember that our goal during the backward pass is to find a derivative of a loss function with respect to parameters here. And parameters here are W, the matrix W. They are stored in this matrix. Which means that I need dl by dw, or, according to our notation, it's just w with this line here. But what do we have as an input of our backward process? We actually have this z with overlined that, which is actually a derivative of a loss function with respect to this view of our signal, right? And to calculate this derivative dl by dw, we actually need a Jacobian here. So we say that we will use this multivariate chain rule. So we can say that w with line is actually, let's say, Jacobian transpose multiplied by this z with line here. Let's verify our notation. Yeah, that's it. You can see this formula for multivariate chain rule. Again, let's verify it according to all the dimensions here. Let's say this vector has dimension as shape n times 1, this has m times n, this has m times 1. Then the gradient with respect to the weights should have the dimension m times n. Okay. These derivatives should have the dimension m times 1, and that's it. We have this, oh, not really, another way, right? Let's write it here. That multiplied by a Jacobian, and yeah, that's it. Am I right? M times n, right? Yes, am I right here? M times 1. Okay. Let me fix it like briefly. Yeah, typically when we are talking about the Jacobian here, it's not a matrix because we have a matrix as an input and a vector as an output. So the Jacobian here actually a tensor, but the overall derivative should be a matrix because of the shape of the W. So let's say, okay, let me leave it for now and I'll return to it a little bit later, because that's not only a thing which I need to calculate during my backward pass. Because if I want this to be modular, I also have to calculate, to propagate this derivative later and calculate x with line also. So I need this and this. So let me say again, x with the bar here should be calculated in a correct way, right here, as it was in the Jacobian form here, Jacobian transposition multiplied by z bar. Let's verify it now. This should be n times 1, this should be m times 1, and this should be transposition here is n times m, which is great, which is correct, right? Okay, so a little confusion was before, but actually I also have to calculate this derivative, and I'll write the correct formula for these derivatives, and I'll leave the proof for you to verify. You can ask me a question about it, but still, that's the correct formula actually. That's that bar times x transposed. Let's again verify it. M times 1, 1 times n. That's it, that's correct. And again, typically, during our backward pass, we are to calculate about twice more objects comparing to the forward pass, because during the forward pass, we just putting all these things together and propagate it further. But when we are going during our backward pass, we have to calculate two derivatives typically. One as like these derivatives with respect to parameters of this exact transformation, and we also have to propagate the error signal later, right, to the previous part of our model to continue backpropagation process. And that's like the rule of thumb here, and typically we think of a backward pass is something which is slightly like longer, like 2 times longer according to this example here, but not all layers are linear, or not all layers are multiplication by a matrix. That's why that's not the strict rule, but some kind of like something to orient to. It's just the backward pass is twice longer, typically twice longer, sometimes 3 times longer, sometimes less than 2 times longer than forward pass. That's it. Okay. But the last, but not the least, idea why do it work so fast is very efficient implementation of this Jacobian vector product. Let's take a closer look here. During our error propagation or gradient propagation, we have to multiply a vector to a Jacobian or a Jacobian to a vector. That's called vector Jacobian product or Jacobian vector product, and actually different order stands for the different approach of automatic differentiation, but that doesn't matter for us like for a moment, but still it's very interesting. And we typically do not construct the Jacobian matrix itself. We are doing matrix to vector multiplication directly, without any storing or constructing Jacobian matrix. That's super important here. For example, suppose you are like taking element-wise exponential here. The Jacobian of this transformation is diagonal matrix, which means that you can multiply this matrix to any vector in a linear time, not a quadratic one as it required by a default general dense matrix, right? And each operation of your computational graph is realized, is made in these automatic differentiation frameworks like PyTorch, like JAX by Google, like Autograd, like TensorFlow. All these implementations are done in a very efficient way. That's why it's so fast. Here are some examples of vector Jacobian product, or VGP, of some very primitive arithmetical functions like addition, subtraction, dividing, and etc. And what is also very important here is the idea of calculating Hessian vector product. This object is very well used in optimization methods of a higher order. For example, a Newton method required the knowledge of Hessian, but again, in order to implement the Newton method, you do not have to store the full Hessian here. You only have to multiply a Hessian by a vector. So the exact formula of a Newton method is following. That's the Hessian matrix inverse multiplied by a gradient vector. And you actually do not need to store the Hessian here or the inverse Hessian here, but you need just the result of this multiplication. And automatic gradient approach allows you to use this idea very efficient, which means that you just formulate the map, and this map takes vector x as an input, and calculate the multiplication of a gradient to this vector, and you just calculate the gradient of this transformation. And the gradient of this transformation actually means multiplication of a Hessian by a vector, or Hessian vector product. So numerically speaking, that's just the exact formula. You just taking this gradient formula here from this like v dot is just the matrix to vector multiplication. So again, gradient of a function multiplied by a vector and gradient of all these. That's the way to implement it. So if you need to use higher order derivatives, automatic differentiation allows you to do it. Let's sum it up. Some key concepts to understand automatic differentiation. First is computational graph. You are building this computational graph, and actually all these libraries, again, like PyTorch, TensorFlow, from the second version, JAX, are building this computational graph under the hood of your computation during the first forward pass. That's actually why the first forward pass could take a little bit more in time than all next runs. Okay, next, first was computational graph. Second is multivariate chain rule and Jacobian vector product. And this should be done efficiently without storing exact Jacobian and multiplying by a general Jacobian. You have to implement very specific Jacobian vector product for each arithmetic operation efficiently. And the third idea here is backpropagation algorithm, which require accumulating of all the gradients from the very end to the very beginning of your computational graph. That's it. Three main things, which are combining, when combining together, forms a very efficient, fast, and reliable way to compute a derivatives with respect to all parameters of your model. Computational graph. Second is multivariate chain rule and Jacobian vector product. Third is backpropagation idea, accumulating all of these gradients. Let's take a closer look at the examples. Here, we'll open this link, which is available on the site. That's the link on the top of the page here. Let's take a look how it can be used actually. And it all started from Autograd library. That's why it is called Autograd nowadays, because initially it was the name of a library for automatic differentiation. So suppose we have a function Taylor sine here, for example, which is a scalar function, and actually we just import from Autograd library grad function. Okay, that's it. That's the grad function here. That's it. Sorry. You just take your function as an input to the grad function, and the grad function will return you a function, grad sine. And you can just call this function at any point you want. And that's actually pretty correct, because that's the Taylor expansion of a sine function, which should be close to a sine function. And the gradient of a sine is a cosine, and the cosine from p should be equal to -1, which is pretty close to computed answer here. Let's take a look at how automatic differentiation is implemented in PyTorch library. That's the example of linear regression with manual gradient computation first. Suppose we have a very simple linear model. This is our linear model. This is our loss function, which is a final referee and jury in our training process here. And that's the manual computation of a gradient. Okay, nothing complex here. We have a learning rate, we have forward pass, which is a prediction, right? We have a loss function computation, we have the manual gradient computation, and manual implementation of gradient descent. Okay, pretty straightforward here. So we have this, okay, we found the optimal value of W. That's okay. What about automatic differentiation here? Most things will remain the same as in the previous task, but let's take a look. Here we have forward pass, loss function computation, and one function to make a backward pass. And during this backward pass, we will get all the gradients with respect to all parameters which were specified in advance. Let's take a look. Here we have defined parameter W, and we explicitly told to PyTorch, we explicitly ask for a gradient here, right? And that's why after I called a backward pass here, I can go to grad field in my object W, and I have a tensor or a matrix or a scalar, it depends on the shape of the W, of gradient here. And again, gradient descent, right? That's gradient here. Next, I'll zero my gradients in order to not to accumulate all the gradients, because typically when you call backward here, you add the new version of gradient to the previous value, which is initially 0, but if you will not zero it by hand, you have an option to accumulate all this gradient, which is not the best way to do. Okay, you also find an optimal value here, that's it, and I recommend you to take a look at the JAX library, which has a very powerful automatic differential framework which fully supports NumPy and offers you a lot of more. For example, if you have a scalar function here, you can take a lot of gradients as that's, for example, a gradient of gradient, then gradient of gradient of gradient of hyperbolic tangents here, and that's a simple way to compute the gradients. But if you have a vector function which takes a vector as an input and outputs a scalar, using this grad approach, you'll receive only the gradient with respect to the first variable here. That's important to know. For example, we have this loss function which was defined here. Here, again, we have defined loss function which depends on W and B, function of two variables, of matrix and vector B. And when we call grad here, we can explicitly specify the variable with respect to which we are taking a derivative here, but by default, that's the first variable. So if you will not specify it, just call gradient of loss, you'll receive a gradient with respect to the first variable. So that's, as you can see, the same thing here. But you can also specify a second variable, for example, a biases and etc. And I recommend you to take a look at this link, which is JAX AutoDiff cookbook, which is pretty interesting reading on the automatic gradient examples and etc. So it's actually pretty long, but it starts from the very beginning, from the very basics of automatic differentiation. That's starting with grad function, then these examples were taken from this notebook. Then you can differentiate with respect to lists, tuples, and dicts, and etc. You can evaluate function value and gradient of this function, actually like forward and backward pass instantly, but nothing, like no magic here happens because it takes time. And all this stuff like Hessian vector products and all advanced stuff like forward mode automatic differentiation, reverse mode automatic differentiation, and etc. So I strongly recommend to take a look at this notebook. That was it for today. Thank you very much.